Myself, Madhuri Modak, Assistant Professor in Mathematics, Department of Computer Science, Aviday Namdar Senior College. Now, in the paper Groups and Coding Theory, we have seen first and second unit. Now, first unit was introduction. In second unit, we have seen definition of group and some examples of finite and infinite groups. Now, we start with the third unit, that is finite groups and subgroups. Now, subgroup. Now we know already what is the meaning of subset. So subset means what? We say that each subset of B if every element of A is present in B, then A is subset of B. Now similar to subset, there is a concept of subgroup. So already we have seen group. Now we are defined subgroup. See the definition. A non-empty subset H of a group G is called a subgroup of G star if H star is itself a group. That is, if H itself forms a group under the same operation of G. In this case, we write that H subgroup of G, and we read this as H is a subgroup of G. Now see the definition. First of all, G with respect to star is one group. Now H to form a subgroup of G, H must be non-empty subset of G. And secondly, H with respect to star must form a group. That means whatever is the operation defined on that group G, with respect to same operation, H must form a group. And at the same time, H is non-empty subset of G. Then we say that H is a subgroup of G. Now, if you consider any group G with respect to star, then that group has always two subgroups. Now, one is the set containing identity only, that is singleton E, and another is G itself, because every set is subset of itself. So, for any group G with identity E, singleton E and G are always subgroups of that group. These two groups are called as trivial or improper subgroups of G. Now, what is proper subgroup? The subgroup of G other than the trivial subgroup is called as proper subgroup. Now, we have seen some examples. See, G equal to 1 minus 1 I minus I. It forms a group with respect to complex multiplication. Now in this case, one is identity element. So if I consider the set containing one only, that is singleton one, and the set G itself, which is 1 minus 1 I minus I, then these are always subgroups of that group G equal to 1 minus 1 I minus I. So these two groups are trivial or improper subgroups of G. Now, if I consider the set containing 1 minus 1, then it is non-empty subset of 1 minus 1 I minus I, and it is itself a group with respect to complex multiplication. So we can say that 1 minus 1 is a proper subgroup of 1 minus 1 I minus I. Now, see, R forms a group under usual addition, means regular addition, R forms a group. Now, Z, that is set of integers, is a non-empty subset of R. And with respect to same addition, Z forms a group. Hence, we can say that Z with addition is a subgroup of R with addition. Similarly, the set of rational numbers Q is a non-empty subset of set of real numbers. Now, R with respect to addition forms a group, and with respect to same addition, Q also forms a group. Hence, we can say that Q with addition is a subgroup of R with addition. This example already we have seen that 1 minus 1 is a subgroup of 1 minus 1 I minus I under complex multiplication. Now, to show that some set H is a subgroup of G, or to check that H is a subgroup of G or not, there are some subgroup tests. Now, theorem 1. One-step subgroup test, that is necessary and sufficient condition for a subset to be a subgroup. Now see the statement. Let G star be a group and H be a non-empty subset of G. Then H is a subgroup of G if and only if A star B inverse is present in H for all AB belonging to H, or a necessary and sufficient condition for a non-empty subset H of a group G star to be a subgroup of G is that AB in H implies A star B inverse belong to H. So whenever you have to show that H is a subgroup of G, first of all H must be non-empty subset of G, and secondly only one condition we have to check, that A star B inverse is present in H for all AB belonging to H. So as there is only one condition, this subgroup test is known as one-step subgroup test. Now see the remark. Even though the same name is one-step subgroup test, we have to actually follow the three steps given below. So first step is show that H is non-empty by verifying that E is present in H. Now in actually one-step subgroup test, we have to check A star B inverse is present in H or not. Now for that we consider two general elements AB in H, and then we check or show that A star B inverse is present in H. So if all these conditions are satisfied, then by one step subgroup test we can say that H is a subgroup of G. Now let G be an abelian group with identity element E. Now here that group is not specified, it is any group which is an abelian group, means commutative group, and H equal to X in G satisfying X square equal to identity. So H contains all those elements of group G whose second power is equal to identity element of that group G. So that H is a subgroup of G. So here we will use one-step subgroup test to prove that H is a subgroup of G. Now, as the members of H are from G only, clearly H is subset of G. Now, to show non-emptiness, we check the element E, whether it is present in H or not. Now, E is an identity element of G. So, E is present in G. Just we check this condition for X equal to E. Now E square is identity because E is an identity element. So this condition is also satisfied by E. Hence E is present in H. So H is a non-empty subset of G. Now to check the condition, we take two elements A and B from H. Now, as A and B are present in H, by definition, A and B are elements of G satisfying this condition. So, X square equal to identity, that condition is satisfied by A and B both. So, we get A square is identity and B square is identity. Now, according to one-step subgroup test, we have to prove that A star B inverse, this element is present in H. Now as A and B are elements of G, A star B inverse is an element of G because G is a group. So only thing is A star B inverse bracket raised to 2 is equal to identity. That part we have to show. So consider A star B inverse raised to 2. Now by definition of integral power, it is A star B inverse star A star B inverse. Now by using associativity of star, because G is a group, it is A star in bracket B inverse star A star B inverse. Now as G is an abelian group, star is commutative. So B inverse star A can be written as A star B inverse. Again using associativity, we get this as A star B inverse star B inverse. Now by definition of integral power, A star A is A raised to 2 star B inverse is B inverse raised to 2, which is A square star B square raised to minus 1. Now as A and B are elements of H, A square is identity, B square is identity. So this is E star E inverse, and inverse of identity is itself. So it is E star E, which is E. So finally we get A star B inverse raised to 2 is identity. So A star B inverse is an element of H. Hence H is the subgroup of G. Now another way of showing H is a subgroup of G is two-step subgroup test. Let G star be a group. A non-empty subset H of G is a subgroup of G if and only if it satisfies following conditions. Now first is A star B is present in H for all AB in H, that is closure property. And secondly, A inverse belong to H for A in H, means inverse exists for every element in H. So whatever is the condition A star B inverse present in H in one step subgroup test, it is splitted here. So first condition is A star B in H and secondly A inverse is in H. So there are two conditions. That's why this test is called as two-step subgroup test. Again, whenever by using two-step subgroup test, we check or show that H is a subgroup of G, then first you have to check for non-emptiness of H and H subset of G, and then we check for these two conditions. Now, one more test is there, that is finite subgroup test. Let H be a non-empty finite subset of a group G. If H is closed under the operation of G, that is A star B is present in H whenever A in H be in H, then H is a subgroup of G. Now, finite subgroup test is applicable only if H is a finite subset of some group G. Now, how to check for subgroup of G or not? If H is closed under the operation of G, that is A star B is present in H whenever AB belong to H, then H is a subgroup of G.